All right, congratulations, you have made it to Chapter 4, Examples of Price Formation with GHG. This is the final chapter of this Evergreen training. We're going to go through 4 examples of how we dispatch resources, attribute resources from a non-GHG area to a GHG area, how we set prices, and make sure that all costs are paid for by those that are responsible for incurring those costs. So as we go through each of these examples, we'll go down our checklist that we came up with in Chapter 1 to make sure that the resulting solution is efficient and aligns with principles of price formation as well as our GHG policy principles. All 4 of the examples that I will walk through can be found in the business practice manuals for the energy imbalance market. If you look at section 11.3.3.2, you'll find the greenhouse gas methodology, and that contains the mathematical formula that we use in the optimization, which I've also put on the screen, as well as examples. And you'll note that the example setup that I have here and that is in the BPMs looks a little bit different visually. It is explained in a somewhat different manner, but all of the numbers are the same. The solutions and the outcomes in this presentation should match those that are in the BPMs. I've just broken it down much more granularly to hopefully help you connect the dots and give you a deeper understanding of what's happening. So before we dive into the examples, I'll take a few minutes to review how I've set this up. If you've already gone through chapters 2 and 3, or you've done that recently, way to go. And you can just fast forward through this section if you'd like. If you haven't gone through 2 and 3, this will provide, or you haven't gone through 2 and 3 in a while, this will provide a refresher for what this looks like. But I do recommend that you go back and do that. But proceed at your own pace. So the 2 areas that we'll look at in these examples are labeled the GHG area and the non-GHG area. Each example will show a transfer constraint, and that's labeled at the bottom. In this example, it's a 100 megawatt transfer. In the GHG area, we see load that's labeled at the bottom as LGHG, and there's one resource, that's Unit 1. Unit 1 submits an energy bid only, which we expect to include the cost of GHG compliance. And as we talked about in Chapter 3, this is because this resource doesn't get attributed to its own area. The LMP in the GHG area will reflect all relevant energy and compliance costs, so there's no need to separate out that energy and GHG. In the non-GHG area, we have 2 resources, Units 2 and 3. Units 2 and 3 do submit separate energy and GHG bids. And we'll assume throughout this presentation that both units or all of the resources in the non-GHG area submit a megawatt quantity bid for attribution for their max capacity. The load in the non-GHG area is labeled LN at the bottom. Both areas have their own LMPs. That's going to be LMP GHG and LMPN. LMP GHG is the price signal for the GHG area resources. So Unit 1 is going to be paid LMP GHG. LMP GHG is the price signal for Unit 1. LMPN is the price signal for Units 2 and 3 in this example. And we figure out what these LMPs are by looking at the load in each area. So we'll uncover LMP GHG by increasing load in the GHG area by 1, and we'll figure out what LMPN is by increasing load in the non-GHG area by 1. In the example on your screen, there's a price separation between LMP GHG and LMPN. And in all of these examples, if we see a price separation, it can be accounted for through some combination of GHG costs and congestion costs. Now, if you're looking at your screen right now and you don't know what's going on, this is the sign that you needed to pause and go back to chapters 2 and 3. In chapter 2, we reviewed where a price difference between LMPs comes from when it comes from congestion, and how we figure out where the price separation comes from GHG. So before we dive in, I just want to provide a final caveat. This is a simplified example. It's intended to help you build the intuition behind GHG accounting and the GHG market design policy. None of these examples require a solver to solve. I did end up using a calculator or an Excel spreadsheet in a few of the examples just to get the math right. A lot of people think I should be good at math, but I mostly deal with Greek letters, so I needed a tool to figure out some addition and subtraction. But in general, you should be able to eyeball the solution to each of these examples. These examples do not illustrate additional aspects of GHG market design policy. For example, we include constraints today that are intended to limit secondary dispatch, which is a term that I haven't really talked about in this presentation and won't be covering in this presentation. What we see in a solver or in market results may look different, because in either case you're going to have a lot more complexity than what you see in these 4 examples. But again, the purpose of walking through these is to give you a foundation of knowledge to draw from when looking at more complex examples or market results. So let's go ahead and jump into example 1. And this starts on page 90 of the BPMs. So here are the 3 resources that we're considering for dispatch. We need to meet a total of 250 megawatts of load. 200 megawatts of load will come from the GHG area, and 50 megawatts of load come from the non-GHG area. And we need to dispatch these resources in a way that minimizes the total cost of the system, given the GHG and the non-GHG area's preferences. So if we try to do this the way that we did at the beginning of chapter 1, we would just go by least cost dispatch. But we do need to be cognizant of the transfer constraint. We also need to think about these separate preferences. So first, let's consider the non-GHG area. Unit 3 is the cheapest to serve non-GHG load at $30 per megawatt hour. So that's the $30 in black on top of that unit. And we can take 50 megawatts of that resource. To serve the GHG area, we can take, we would want to take 200 megawatts from Unit 2, but we end up hitting that transfer constraint. We can only take a total of 150 megawatts from the non-GHG area. That's 50 megawatts to meet non-GHG area load, and 100 megawatts brings us to our transfer constraint, which means we'll have to take the final 100 megawatts that we need to meet load in the GHG area from Unit 1. And I've summarized that here. 50 megawatts at $30 per megawatt hour minimizes costs for the non-GHG area. 100 megawatts from Unit 2 minimizes costs for the GHG area and respects that transfer constraint. And the final 100 megawatts that we need will come from Unit 1. So how do we set prices? We do this by considering the GHG and the non-GHG area separately. So first, let's look at the GHG area. Right now, we're meeting 200 megawatts of load. If we needed to meet the 201st megawatt of load, we still have this transfer constraint, which is in our way, so we'll need to take 101 megawatts from Unit 1. That increases the total cost of the system by $50 per megawatt hour, and that's going to be the LMP in the GHG area. Next, let's consider the non-GHG area. If we increase load to 51 megawatts, then we can actually take the next megawatt from unit 3. Remember, we can dispatch up a total of what we need to meet load as well as the transfer constraint. So when we increase load by 1, that means we can dispatch up a total of 151 megawatts in the non-GHG area, and our marginal unit is going to be unit 3, and I've reflected that on your screen. Before we move forward, let's check to see if prices so far are efficient. Unit 1 responds to LMP GHG. We only need 100 megawatts of Unit 1, so we shouldn't expect it to receive any surplus payment for this LMP, and indeed it does not. It is indifferent to dispatching across its operational range. LMPN is the price signal for Unit 3, and that's the same thing here, where it's the marginal resource, and so we should expect it to make 0 profit from the LMP in the non-GHG area. Now, Unit 2 also responds to LMPN, but as you can see, LMPN is not a sufficient or complete price signal for Unit 2. And that makes sense because we're dispatching Unit 2 to 100 megawatts, and all 100 megawatts are being included in the export allocation, which I've noted in the gray box at the top. All of the capacity that we are taking from Unit 2 are being attributed to the GHG area. So Unit 2 should be responding to a different price signal than just LMPN alone. And that's going to be the marginal cost of GHG. Now, in Chapter 2, we walked through how to verify what the marginal cost of congestion is. We would increase this transfer constraint from 100 to 101. If we did that, we'd be able to dispatch down 1 megawatt from Unit 1, dispatch up 1 megawatt from Unit 2, for a total savings to the system of $15 per megawatt hour. So that's how we would verify what the marginal cost of congestion is in this case. We can similarly verify what the marginal cost of GHG is in this case, the way that we did in Chapter 3, where we look at this export allocation, which right now is 100 megawatts. If we reduce that to 99 megawatts, but we don't change the power balance constraint, that means we would need to meet 199 megawatts of load in the GHG area and 51 megawatts of load in the non-GHG area. When we do that, we would dispatch down 1 megawatt of Unit 2, dispatch up 1 megawatt of Unit 3, and when we do that, it's serving the non-GHG area, so that's going to cost $30 per megawatt hour and give us a total savings of $5. So that's one way of verifying that this is what the marginal cost of GHG is. But I've also organized this so that you can see visually that this is an efficient price signal, and I've broken it down in a couple of slides to understand how this funds resource costs and where that money comes from. So just from a visual perspective, we know that Unit 2 is the marginal unit serving the GHG area from the non-GHG area. So this resource is attributed. It responds to not only the price signal LMPN, but also the marginal cost of GHG. So its combined price signal, LMPN plus the marginal cost of GHG, is its price signal. For this to be an efficient price signal, we want that price to be equal to this resource's bid price. Because it's the marginal unit, we don't want it to make any surplus profit because we don't need any more of it than 100 megawatts. We also want it to respond, so we know it needs to be something higher than $30 per megawatt hour. $35, therefore, is the efficient price signal for Unit 2. So I've broken all of this down so that you can match this with what's in the BPMs This is just a high-level summary of what we just found on the previous slide. And the thing that I'll highlight is at the bottom here, where in green on the previous slide, I noted that there was a 100 megawatt export allocation, and I'll show you how we come up with these revenue numbers. 100 megawatts of an export allocation times the marginal congestion cost gives you $1,500 in congestion revenue. A 100 megawatt export allocation times the marginal GHG cost gives you $500 in GHG revenue. So let's talk a little bit more about these price signals to determine if they're efficient and how this really works. The price signals that are relevant to dispatching GHG are LMP GHG and the combined price signal LMPN plus the marginal cost of GHG. So this top row, we see that Unit 1 is dispatched to 100 megawatts. Its bid price is $50 per megawatt hour, and we assume that that bid price includes its compliance costs, but so does LMP GHG, and this is an efficient price signal for this resource. And now, we do see that LMP GHG and LMPN plus the marginal cost of GHG are different numbers. And that's because we have a transmission constraint, which creates price separation between these areas. But you can think of both LMP-GHG and LMPN plus the marginal cost of GHG as the relevant price signals that we want to look at here. LMPN plus the marginal cost of GHG, that combined price signal, is only relevant to resources that receive a GHG export allocation. So if we look at Unit 2, it's dispatched to 100 megawatts. It receives a 100 megawatt export allocation, and therefore we care about whether this price signal is efficient for this resource. The resource's bid plus compliance totals $35 per megawatt hour, and we see that the price signal, LMPN plus MCGHG, is also $35 per megawatt hour. And this is an efficient price signal for this resource. We can also take a look at Unit 3. Unit 3 does not receive an export allocation, so it's not responding to LMPN plus MCGHG, but even if it did, we would see that LMPN plus MCGHG is not a sufficient price signal for this resource, and this resource is not economic to serve the GHG area at a combined energy plus compliance cost of $36 per megawatt hour. So now let's talk about just the price signal for non-GHG area resources that are serving the non-GHG area. There are two non-GHG area resources, Units 2 and 3, and we're just going to consider their bid prices. Because when we consider resources for the GHG area, for the non-GHG area, we want to remove that bid adder. So when we do, the bid price for Unit 2 is $35 per megawatt hour, and the bid price for Unit 3 is $30 per megawatt hour. Both of these resources are going to respond to LMPN, which is $30 per megawatt hour, and they'll receive a total energy payment from LMPN of 30 times their dispatched quantity. So we see the total cost of Unit 2 is $3,500, but it only gets $3,000, that's 100 megawatts dispatched, times LMPN from this price signal. So it receives a negative excess energy payment, or it's in the hole here. LMPN is not sufficient to cover this resource's energy costs. Unit 3 is only being used to serve the non-GHG area. It costs $30 per megawatt hour. It responds to a $30 per megawatt hour LMP. 50 megawatts times $30 per megawatt hour means the total cost of this resource is $1,500. And that's what it receives from this LMP. So this resource is made whole by LMPN.
Okay.
So before we move on, let's focus on this negative 500 here. Unit 2 is not dispatched to serve the non-GHG area, but we still want it to be made whole. So we need to make sure that it gets its excess energy covered. And that's going to come from revenue from the export allocation. So we're just going to focus on Unit 2 here. Unit 2 is dispatched to 100 megawatts, and it has a 100 megawatt GHG export allocation. All export allocations receive a GHG payment for that export allocation. So if we saw Unit 3 get an export allocation, there would be something in the column labeled GHG export allocation, and we'll see that later on. But for now, it's only Unit 2. It gets a 100 megawatt export allocation. So we multiply 100 by 5, that's the marginal cost of GHG, and that tells us the total GHG payment this resource will receive. Now this was a clean resource, so it's emitted a GHG bid adder of 0, which means it doesn't have any compliance costs. But as we saw in the previous slide, it didn't make enough money from LMPN. So while it doesn't have any compliance costs, it still receives this payment, and the payment in excess of its compliance is $500. That is going to be used to make this resource whole. And this slide summarizes the total cost of each of these resources to make sure that we know all of these costs are being covered and where they're getting covered from. So LMPN was insufficient to cover the full energy cost of Unit 2. Recall that LMPN is $30 per megawatt hour times 100 megawatts dispatched only gives us $3,000. But the total energy cost of this resource is $3,500. So it's in the whole 500, but it receives $500 in a GHG payment, and that makes this resource, that makes sure this resource is fully covered. The first time I went through this confused me a little bit because I was thinking, wait a minute, it's responding to LMPN, and LMPN is funding most of this resource's energy cost. But what's actually happening is that load only pays for what they're responsible for. So the LMP is the price signal for these resources, but we're going to start at the end here to see how each area actually pays for its capacity. So load in the GHG area was 200 megawatts. The price signal in the GHG area is $50 per megawatt hour. So the total payment funded by load in the GHG area is going to be $10,000. Similarly, we've got 50 megawatts of load in the non-GHG area. The LMP in the non-GHG area is $30 per megawatt hour, which means the total payment funded by load in the non-GHG area is $1,500. And so the total that we're collecting from load in the market is $11,500. That's also the total that we need to cover the cost of units 1, 2, 3, and congestion. But we're going to use this money to only cover the costs that each load is responsible for. So of that $10,000, we'll start at the beginning of this chart now, and we'll use that money to cover the total cost of Unit 1, the total cost of Unit 2. We don't use it to cover any costs of Unit 3 because that wasn't economic to serve the GHG area, and load in the GHG area covers the cost of congestion. Finally, we use all $1,500 of the payment funded by load in the non-GHG area to cover the cost of Unit 3. Okay, now we're going to move on to example number 2. So this is a very similar problem as before, with one important difference. Unit 3 in the previous example submitted an energy bid of $30 per megawatt hour and a GHG bid adder of $6 per megawatt hour in compliance costs. In this case, Unit 3 submits an energy bid of $28 per megawatt hour and a GHG compliance cost of $6 per megawatt hour, which means the combined price of Unit 3, if we're considering it for transfer to the GHG area, is now cheaper than Unit 2 at a total of $34 per megawatt hour, which means instead of dispatching up 100 megawatts of Unit 2, we're going to take 100 megawatts of Unit 3 for transfer to the GHG area. So we'll dispatch a total of 150 megawatts from Unit 3. 50 we'll consider as serving the non-GHG area, so 50 megawatts of Unit 3 will cost $28 per megawatt hour. 100 megawatts of that same resource cost $34 per megawatt hour, and the the GHG area will be responsible for paying for that. So how do we find LMPs? We do this the same way as we did before. The LMP in the GHG area stays the same. In the non-GHG area, if we needed to meet 1 additional megawatt of load, we would dispatch up Unit 3 at $28 per megawatt hour. So the difference in LMPs between the GHG and the non-GHG area is total $22, and that's made up of some combination of congestion and the marginal cost of GHG. We can figure that out the same way as we did before. We can increase the transfer constraint from 100 to 101, and we find that the savings to the system from dispatching down Unit 1 and dispatching up 1 megawatt of Unit 3 is going to be $16 per megawatt hour, which means the marginal cost of GHG ends up being 6. So you can go through the motions of figuring out what the marginal cost of GHG is by reducing the export allocation from 100 to 99, but we can also once again see it visually here, where the marginal unit for both the GHG and the non-GHG area in the non-GHG area is Unit 3. So we don't want this resource to have any additional, to accrue any additional revenue beyond its bid price. So the LMP of 28 is an efficient price signal for Unit 3. An LMP of 28 plus 6, that gives us $34 per megawatt hour. That's an efficient price signal for resources being considered for the GHG area. And I've summarized that once again here, but let's break this down price signal by price signal to confirm that all of this is efficient. So once again, the Unit 1 is in the GHG area. Its bid price, which we assume includes compliance, is $50 per megawatt hour. It responds to LMP GHG, which is also $50 per megawatt hour. And this is an efficient price signal for that resource. In the non-GHG area, all 100 megawatts of the 100 megawatt export allocation go to Unit 3 this time. So we don't need to consider whether or not LMPN plus the marginal cost of GHG is an efficient price signal for Unit 2, but you can also see that it's not. It won't incentivize, or it is efficient, but it won't incentivize any capacity from Unit 2. So that checks the box for that resource. Unit 3 is attributed to the GHG area, so we want to make sure that the combined LMPN plus marginal cost of GHG is an efficient price signal for this resource. So the energy bid plus compliance is 34. The combined LMP plus marginal cost of GHG is 34. And so this looks like an efficient price signal without us having to do anything else. Now let's check that prices in the non-GHG area are efficient. We are just considering the energy bids, not energy plus compliance. So Unit 1 submits an energy bid of $35 per megawatt hour. Sorry, Unit 2 submits an energy bid of $35 per megawatt hour, and Unit 3 submits an energy bid of $28 per megawatt hour. The LMPN is 28. So resource 2 does not have an incentive to put any of its capacity on the grid. Resource 3 does, but it's indifferent across its operational range, so it has its total costs covered, and this is the right price signal for that resource. So in the previous example, we saw that the export allocation, or all export allocations, received a GHG payment, but that GHG payment in example 1 was used to cover energy costs in excess of what was signaled through LMPN. This looks a little bit different, so let's focus on Unit 3. It gets dispatched to 150 megawatts total, but the export allocation is just for 100 megawatts. For that 100 megawatts, we're going to multiply that by the marginal cost of GHG, and that gives us a total GHG payment of $600. Recall that the GHG bid adder on this resource was $6, which means its total GHG compliance cost is $6 times the 100 megawatts we're attributing, so $600. All $600 of this GHG payment are used to cover this resource's GHG compliance costs, which means we don't have any payment in excess of compliance. But that makes sense because in the last example, all of the GHG payment was in excess of compliance, and we needed that to cover excess energy costs. In this case, we don't. We just need the GHG area to take responsible for all of its compliance costs. So here we see the total cost of the resources that were being dispatched. Unit 1 is dispatched to 100 megawatts, so the total cost of this resource is $5,000. And this is the total cost that is signaled by LMP GHG. We don't need any of resource 2, so let's look at 3. We dispatch Unit 3 to 150 megawatts. 150 megawatts of resource 3, if we just consider energy, is $4,200. But if we add the $600 compliance cost onto that, the total cost of this resource is $4,800. It doesn't receive any excess energy payment from either area, but it does receive a GHG payment, and that makes this resource whole. So finally, let's make sure that load in the GHG area and load in the non-GHG area are paying for what they are willing to pay for and what they're responsible for paying for. So once again, let's start at the end where I've labeled load and LMP. So load in the GHG area is $200, which means 200 times the LMP there, $50 per megawatt hour, gives us a total of $10,000 that are funded by load in the GHG area. And that's used to cover the total cost of Unit 1, the cost of 100 megawatts of Unit 3, including its compliance costs, and congestion. 50 megawatts of load in the non-GHG area must pay $28 per megawatt hour. So the total payment funded by load in the non-GHG area is $1,400, and that is sufficient to cover the total energy cost of 50 megawatts of Unit 3. All right, let's move on to example 3. Fair warning, things are about to get a little bit spicier. All of the bids in this example are the same. The one thing that I have changed here is that I have reduced the total capacity that's available, both in terms of energy and what can be attributed to the GHG area, to 75 megawatts, which means we can send 75 megawatts total from this resource to the GHG and non-GHG areas. And here's how we break that down in least cost. So we still have a transfer constraint from the non-GHG area to the GHG area. That means we can only dispatch up a total of 150 megawatts from the non-GHG area. The cheapest resource for both the GHG area and the non-GHG area is going to be Unit 3. So we'll dispatch that up to its max, which is 75 megawatts. And then we know that we'll take the last 75 from Unit 2. How have I broken this down here? Why did the GHG area get saddled with Unit 2, whereas the non-GHG area got to be covered by Unit 3, which is the cheapest for both of them? Well, using Unit 3 to serve non-GHG area load saves the total system cost, saves more money in terms of the total system cost than we would have had we done this a different way. So you can imagine we used all 75 megawatts from Unit 3 to serve the GHG area. But if we had done that, it would have cost us an extra $7 per megawatt hour to use Unit 2 to serve the non-GHG area. Whereas in this solution, it only costs an extra $1 to use Unit 2 instead of Unit 3 to serve the GHG area. So this combination of resources serving the GHG and the non-GHG areas is the way that we minimize the total cost of the system in this scenario. So how do we set prices? Well, we can start with the easy one. If we increase load in the GHG area from 200 to 201, the 101st megawatt would come from Unit 1 at $50 per megawatt hour, and that sets the LMP in the GHG area. What about the non-GHG area? Well, I'm actually going to cut to the chase here and tell you that the LMP in the non-GHG area is 29. And this took me a minute to really wrap my head around. So I've created another slide to explain this to you. And in the appendix, there's yet another way that you might understand it. And the BPMs also provide another way to understand it. But I like to think of this as a negotiation. So why is the LMP in the non-GHG area $29? Well, if we consider these two resources from the perspective of the GHG area, Unit 2 costs $35 and Unit 3 costs $34 per megawatt hour. If we consider these two resources from the perspective of the non-GHG area, Unit 2 costs $35 per megawatt hour, and Unit 3 costs $28 per megawatt hour. So when we need to meet an additional megawatt of load from the non-GHG area, the question is, how do we resolve this solution? How do we dispatch up these resources? So do we take an additional megawatt from Unit 2, or do we take an additional megawatt of Unit 3? Well, if we take an additional megawatt of Unit 2, that would cost the system $35. If we took an additional megawatt from Unit 3, that would cost the system $28. So we're going to end up taking an additional megawatt from Unit 3 at a total system cost of $28. But What that does is it forces 1 megawatt of capacity that we were using to serve the GHG area to move from Unit 3 to Unit 2. And load in the non-GHG area has to pay for that. So load in the GHG area is willing to pay an additional $1 per megawatt hour to make that switch. Load in the non-GHG area would have to be paid an extra $7 per megawatt hour in order to make this switch. So the way that we minimize costs here is for load in the non-GHG area to make up that difference, to make the GHG area indifferent to switching from Unit 3 to Unit 2. So if you go to the appendix, I walk through another way to think through this redispatch situation. And the BPMs also explain how we would redispatch these resources when you increase load in the non-GHG area by 1 megawatt. In any case, the $1 above Unit 3's bid price, you can think of that as a scarcity signal or an opportunity cost. It says, we need more of you, but this is the additional profit to this resource that would minimize the total cost of the system. So when we go back here, we see that the LMP in the non-GHG area is $29, and the marginal cost of congestion is $15 per megawatt hour. Our marginal cost of GHG is 6, which means the total price signal on Unit 3 is now 29 plus 6, so $35 per megawatt hour. Here's a summary of all of those things, and we see that GHG revenue in the previous two examples were allocated just to a single unit. So now we're going to see how GHG revenue is efficiently allocated to cover both energy costs and compliance costs in excess of LMPN. First, let's start with the price signal for GHG area resources. We've talked about Unit 1 already, so let's talk about Unit 2 here. The energy plus GHG bids of Units 2 and 3 are $35 and $34 per megawatt hour, respectively. And since both of them receive a GHG export allocation, we'll consider how the combined LMPN plus marginal cost of GHG is as a price signal to these resources. At $35 per megawatt hour, this is telling Unit 2 that we need you, but we don't need more of you. So Unit 2 is indifferent to dispatching across its operational range. This price signal offers an extra $1 per megawatt hour to Unit 3, and this tells this resource that we need you and we could use more of you. You provide value to the system. So it makes sense that this resource would get an extra $1 per megawatt hour. What I think is interesting is that extra $1 per megawatt hour isn't funded by the GHG area, but the non-GHG area. So let's see that on the next slide. The price signal in the non-GHG area is the price signals for resources serving load in the non-GHG area, and that's going to be $29 per megawatt hour. We're only considering the energy bids of Units 2 and 3, so let's compare each of those energy bids to LMPN. $35 per megawatt hour is higher than LMPN, so even though the total energy cost of this resource is $2,625, it would only receive a payment of $2,175 from LMPN, and so it's going to need to get its excess energy covered by GHG revenue. Now let's think about Unit 3. Unit 3 is dispatched to a total of 75 megawatts, and that's its full capacity. Its energy bid is 28. It faces LMPN 29, and this is a sufficient price signal to get this resource to dispatch to its full capacity, and it receives an extra payment. The total energy cost of this resource is $21,000, but it actually receives a payment of $2,175, and that's a $75 excess payment from LNPN. And this ends up reducing the cost of this resource for the GHG area. But remember that this is a negotiation, so load in the non-GHG area is willing to pay a little bit more for this resource to avoid having to pay an additional $7 per megawatt hour for Unit 3 compared to Unit 2. And the GHG area is willing to accept that $1 per megawatt hour to be indifferent to that switch. So this is the way we minimize system costs for both load in the GHG and the non-GHG area. Before we go onto the next slide, we'll look at this last column, excess energy payment, and remember that we need to cover compliance and energy using GHG revenue. So let's look at units 2 and 3. We dispatch unit 2 to 75 megawatts, and all 75 megawatts get a GHG export allocation. Just like we've done in the previous two examples, let's multiply the GHG export allocation, 75, by 6, and that gives us $450. We don't need to cover any GHG compliance costs, so all $450 of this GHG payment will go toward the energy payment in excess of LMPN. Now let's look at Unit 3. We dispatch 75 megawatts of this resource, but only 25 are attributed to the GHG area. So we multiply 25 by 6, and we get a GHG payment of $150. The GHG bid adder on this resource is 6, which means its compliance costs are also $150, and all of the GHG payment for this resource is used to offset those GHG compliance costs. Finally, let's make sure that all of our resources are being made whole at the very least, and inframarginal resources are being paid some extra profit. Unit 1, this is the same as before. It's dispatched to 100 megawatts. It costs $5,000, and it receives a $5,000 payment from LMP GHG. Unit 2 is dispatched to 75 megawatts. It has a total cost of $2,625. LMPN only covered some of this payment, but the rest comes from the GHG payment, and so this resource is made whole. Finally, Unit 3 is dispatched to $75. The total cost of this resource is $2,100, but it also has a GHG compliance cost on 25 megawatts of the resource, so the total cost of this resource is $2,250. It receives an excess energy payment from the non-GHG area and receives a GHG payment from the GHG area. So at the end of the day, this resource is paid more than its total cost. Its total cost was $2,250. It receives a total payment of $2,325, and that's because we don't have enough of this resource. If we had more of it, we'd be able to reduce the total system costs. So this is that surplus payment that goes to Unit 3. Finally, let's check to make sure that everyone is paying for what they're supposed to be paying for. Load in the GHG area funds $10,000, and that's used to cover all of Unit 1, all of Unit 2, and 25 megawatts of Unit 3 plus its compliance costs. Load in the non-GHG area funds $1,450, and that's used to cover 50 megawatts of Unit 3, just considering its energy payment as well as that additional $1 per megawatt hour in opportunity costs. We've made it to example 4. This one's my favorite example. And that's because we've changed a couple of things here. One of the things that we've changed is that we've added a unit. So now we have Unit 4 in the non-GHG area. Unit 4 costs $30 to the non-GHG area, but $33 to the GHG area. So it's not the cheapest resource to the non-GHG area, but it would be cheaper than Unit 2 and Unit 3 for the GHG area. I've also increased the transfer constraints, whereas before we could only take a total of 150 megawatts from the non-GHG area. Now we'll be able to take a total of 250 megawatts from the non-GHG area to serve the entire market. So how do we solve this problem? Because we no longer have a transfer constraint, we don't need to use Unit 1 at all. The least cost resource for the non-GHG area is going to be Unit 3, just like last time. So we'll take 50 megawatts of Unit 3 at $28 per megawatt hour. The cheapest resource for the GHG area is now Unit 4. So we'll take 100 megawatts from Unit 4 at $33 per megawatt hour. Then we'll take the remaining 25 after we used 50 for the non-GHG area. And then the final 75 that we need will come from Unit 2. So, how do we set prices? If we increase load in the GHG area by 1 megawatt, that next megawatt would come from Unit 2 at $35 per megawatt hour. So the LMP in the GHG area is going to be $35 per megawatt hour. If we needed 1 additional megawatt for the non-GHG area, we would do the same thing as we did before, where we would actually take that from Unit 3. But the non-GHG area still owes the GHG area that $1 to make it worth it to force the GHG area to dispatch up 1 megawatt from a different resource. So the LMP in the non-GHG area is once again going to be 29. So now we have a price difference, but it's different from last time. We no longer have a marginal cost of congestion. So this entire price difference of $6 is going to be made up of the marginal cost of GHG. And let's check visually that this makes sense. With the marginal cost of GHG of $6, that gives us a total combined price of $35 per megawatt hour, and that matches our marginal unit in the non-GHG area. It also provides a surplus payment to both units 3 and 4, and we've used the full capacity of units 3 and 4. So we want to make sure that they receive a surplus payment or price signal that sufficiently incentivizes these resources to dispatch to their full capacity. And they get that price signal that says, if we had more of you, we would use it, and that would reduce the total system costs. So here's the summary, and you'll note that we don't have a marginal congestion cost, which means there's no congestion revenue. The revenue that we do produce is for a 200 megawatt export allocation. So 200 times 6 gives us a total GHG revenue of 1,200. So let's see that the price signal for resources serving the GHG area is correct. Unit 1 submits an energy bid of $50 per megawatt hour, but the LMP in the GHG area is now $35 per megawatt hour, and that's an efficient price signal here because we don't want Unit 1 to dispatch any of its capacity. If we did, we would lose $15 per megawatt hour, and that's not good. So this is an efficient price signal in that case. All 3 units in the non-GHG area receive some GHG export allocation. So we do want to make sure that their energy bid plus compliance compared to the LMP plus marginal cost of GHG, we want to make sure that this is an efficient price signal for them. So in the non-GHG area, Units 2, 3, and 4 are all economic to serve the GHG area. Unit 2, the marginal resource, makes 0 profit. Units 3 and 4 receive an additional profit given that we're using their full capacity. So this is an efficient price signal there. In the non-GHG area, the only resource that we're dispatching up to actually serve the non-GHG area is Unit 3. So let's compare the energy bid 28 to the LMP 29. If we had more of Unit 3, that would be able to reduce the total system costs. So this is an efficient price signal for that resource. And load in the non-GHG area is willing to pay a little bit more for it to make sure that it gets to keep that marginal unit instead of the GHG area. So this resource receives an excess energy payment of $75. Similar to what we've seen before, units 2 and 4 have energy bids in excess of LMPN. So they're going to need $450 and $100 respectively in order to be made whole. But these resources are also not being dispatched to serve load in the non-GHG area, so we'll make that up through the GHG payment. All export allocations receive a GHG payment for that export allocation. So going row by row, starting with Unit 2, Unit 2 receives a 75 megawatt export allocation, so 75 times 6 means that this resource will receive a $450 GHG payment. It doesn't have any compliance costs, so the total of that payment will be used to cover energy costs in excess of LMPN. Unit 3 receives a GHG export allocation of 25 megawatts. So 25 megawatts times 6 gives us a total GHG payment of $150. It also submitted a GHG bid adder of $6 per megawatt hour, which means its GHG compliance is $150. So Unit 3 uses all of its GHG payment to cover its GHG compliance costs. Finally, let's look at Unit 4. Unit 4 receives a 100 megawatt export allocation. Times the marginal cost of GHG gives us $600. Now, this resource does have a GHG bid adder that's $3 per megawatt hour, which means it has a total compliance obligation of $300. So it's going to use just half of this GHG payment to cover those compliance costs. And the other half, so $300, is a payment in excess of compliance. And we saw on the previous slide that this resource needed $100 to be made whole. So it's getting a payment in excess of both compliance and energy. And we can see that here. Resource 4 has a total cost of $3,300. It needs an additional $100 in order to cover excess energy. So this $600 energy payment goes to cover GHG compliance costs, excess energy costs, and it gets a little bit of additional profit margin for being an inframarginal resource. Unit 3 also gets an additional payment over its total cost. The total cost of Unit 3 is $2,250. It receives a total energy payment of $2,325. And again, that's because this resource is an inframarginal unit. And if we had more of it, we'd be able to reduce the total cost of the system. Finally, let's make sure that everyone who's willing to pay for this stuff is paying for this stuff. So if we look at load in the GHG area, we've got 200 megawatts of load, and now the LMP is 35. So the total payment funded by load in the GHG area is $7,000, and that's going to be made up of the total cost of Unit 2, a portion of the cost of Unit 3, and the total cost of Unit 4. Load in the non-GHG area, that's 50 megawatts, faces a price of $29 per megawatt hour, so load in the non-GHG area funds $1,450 in energy payments, and that goes to Unit 3 to cover energy costs as well as that extra $75. Finally, some takeaways. So we've gone through all of these examples, and I encourage you to poke back through and see if you can and see if there's other ways that make sense to you, but these are the real takeaways that I wanted to highlight. When determining if prices are efficient in the non-GHG area, the only thing we care about is what the energy bid and the LMPN are. So in this example on the screen, LMPN is $29 per megawatt hour. We compare that to the energy bid, 28, to figure out if that's efficient. When determining if prices are efficient in the GHG area, we compare the combined energy and GHG cost of allocated resources to LMPN plus the marginal cost of GHG. So we did this in the last example where 3 resources submitted energy plus GHG compliance, and all of those received an expert allocation, and we compared all of them to LMPN plus the marginal cost of GHG. Finally, the LMP in the GHG area and energy bids in the GHG area already reflect a compliance cost, so we didn't need to have to do any math. That already worked out when we considered those price signals. Finally, the marginal cost of GHG tells us revenue that was funded by the GHG area and that gets allocated to resources in the non-GHG area to cover all compliance costs and energy in excess of the price in the non-GHG area. And this ensures that load in each area pays only for what load is willing to pay for and what load is responsible for. And that's it for now. So just a reminder that the full PDF of this presentation can be found on the ISO Stakeholder Initiative page for Greenhouse Gas Coordination Working Groups. And if you have any questions about this, need us to explain it, or you want us to discuss it during a working group, or you need us to clarify something, let us know. Send an email to isostakeholderaffairs@kaiso.com with GHG price information in the subject line. And there should be an appendix attached to this presentation. So anywhere where I've noted you can find more in the appendix, that's there for you to peruse.